this lab, we're going to explore container orchestration. So when people start with containers, they tend to think about a single node, and it's easy to get your brain around it because you think about running MySQL and Apache web server on the same node. It's actually very easy, right? It's just like we've always done. They're just two processes running on the same box. This is what we've done for 10 years, 15 years in the LAMP stack world, right? So this is easy because the developer knows where to push their code. There's a directory somewhere on the server that's bind mounted into the Apache container. The developer also knows where, they can connect to port 3306 and, import data in MySQL. That's easy. The user knows exactly to come to port 443 or port 80, and everything works just like we'd understand it, right? But what happens when we add either two different web servers or two different nodes? Everything falls apart, right? We don't know where to connect to. The users don't know which port to connect to because you can't run both of them on port 80. So now maybe one's running on port 80 and the other's running on port 81. And users will never connect to the port 81 web server. On the other side, the MySQL, what if the other node dies and MySQL moves back to the same server where the Apache servers are running? The developer doesn't know where to import their data. They don't know where to push their data for the web server, and everything becomes a nightmare. So the smart, crafty person in you says to yourself, well, wait a minute, I can fix that. I can write some automation that talks to the load balancer and updates, basically goes out and checks all the nodes in my cluster and then updates the load balancer when it sees, up, and then actually even tells the Apache web servers to start on a different node if a node's dead, blah, blah, blah. We can also, think to ourselves, all right, well, we can use an NFS server, something tricky like that, to have like different, directories for the different web servers and different directories for the MySQL servers. So we might have like HTTPD 01 and HTTPD 02 and 03 and 04. But we could quickly imagine that becomes a nightmare trying to like map out all these different directories on an NFS server, or worse, handling volumes on an iSCSI share, creating volumes on an iSCSI LUN and then formatting them and then and then wiping them after they're done. And you can imagine that becomes a lot of work. So that's why container orchestration. You think about something like Kubernetes or OpenShift, it handles two very distinct problems. It handles the orchestration problem and it handles the application definition problem. The container orchestration problem is nice because now I can add one node or 1,000 nodes. It really doesn't matter. They're all handled identically, and the container orchestration handles the storage, the networking, and all of these things for me. On the application side, there's a definition file, a YAML file that we can use to define the volumes and what we need. We can define how the applications should talk to each other on what ports and how, and role-based access controls are handled for us. And essentially, Kubernetes and OpenShift standardizes everything, and this makes it very, very convenient. So I want to walk through what an example, OpenShift install looks like, just to get your brain around this. So this is a very standard OpenShift install that the OpenShift installer can install out of the box. You just add 3 master nodes, you add 3 worker nodes, and basically you have a load balancer in the front that basically balances the traffic to the master nodes. This is, again, the developer, the administrator hitting the API. At the other end, we have storage that is used for the registry server, and this is kind of what it looks like out of the box. Now, going back to the chaos that we described before, where you'd have to handle all this yourself, etcd handles the state of all these things, right? So like the OpenShift master keeps track of all this stuff and saves it in a distributed database, distributed data store, etcd, across all the master nodes, right? So that makes it very easy. You don't have to handle any of that problem yourself. On the worker nodes, the kubelet basically, talks back and forth with the OpenShift master, and basically talks to Dockerd, which then talks to Containerd, which talks to runc, which I walked through in one of the earlier labs, and essentially fires up, tells the kernel to fire up these containerized processes. Infrastructure can also run things like registry server, router, things like that. Can even distributed storage like cluster for the applications can all live natively inside of this cluster, and Kubernetes/OpenShift schedules all this for you. And you don't have to worry about it. Once you have, multi-master, OpenShift masters, you're good because you're protected from any kind of failures, and you can trust that the cluster will stay in sync and know what it's doing. Now let's get to the application definition, right? So the application definition, these are all the objects it can use to describe how applications should interact and how they should be built and how they should be deployed. And it's a really, really elegant way of describing your applications. Kubernetes is a little bit of a brain bender when you first get into it, because there is a lot to defining an application, right? It does take a certain level of complexity to make it happen. But what I did here is I tried to map real world things that you already understand to these objects inside of Kubernetes OpenShift, and basically kind of make the speed bump small. So we all understand how a container host works and how a registry server works and how a load balancer works. These are things that we're used to doing today. They're really not that different than what we're doing today without containers. They're just processes firing up on a kernel. There's ports, there's TCP ports, there's mounts, there's all these standard objects that you'd understand if you work with Linux, right? Load balancer is the same thing, really. Pretty much most people understand how a load balancer works. You put IPs in a load balancer. That load balancer then forwards traffic, usually HTTP or other protocols, to an application. And the registry server, as I defined in an earlier lab, is basically a fancy file server. So now let's walk kind of left to right from a build, and then let's walk through a deployment and show you how elegant these work. So a developer, would hit the API using essentially tell the API and pass it a configuration file called a template or just a bunch of objects in a YAML or JSON file that define an application. And the highest level kind of objects are the build config and the deployment config. The build config can contain all the definitions for the other objects within the build kind of group of objects, and same with the deployment config. So from a build config is essentially an object that defines how to kick off builds, and then when builds fire off, there's actually a build in the system, and you'll see it like an OC get builds will show you all the actual instantiated builds at any given time, and you'll see build 1, build 2, build 3, and there's they'll be numeric, they'll increment because there'll be more and more builds as time goes on. And each one of these builds essentially kicks off a pod, and inside of that pod, it can do magical things, like do a Docker build or do a source to image build. And there's different types of builds that can happen. But when it's done, what it does is it actually creates an image object. That image object represents an actual image that gets pushed into the registry server. And then it actually triggers a new tag to be created in what's called an image stream. And think of the image stream as a spider web. Anytime it's triggered, it can, the spider can come out and eat the bug. It can actually kick off other automation to happen inside of OpenShift. The first type of automation would be triggering another build. The second type would be triggering an automated deployment. When you trigger an automated build, you could do what I mentioned before in one of the previous labs, is do cascading builds, right? So the core build, when it's completed, it could trigger the image stream and say, hey, I've got a new version of the core build, go build everything else that depends on me. And then you could trigger, a new Ruby build, a new Python build, a new database build, a new anything build. So you can essentially cause cascading builds to happen, and you can have these go as deep as you want. I don't generally recommend going too deep, more than maybe 3 or maybe 4, because it gets hard for human beings to understand how this automation is kicking off other things. But you can imagine you can do a couple, cascading builds, and at some point, you'll be at kind of the leaf node build where, okay, now it's time to deploy an application. Now it's time to deploy the database or deploy the Python application, and then the image stream can trigger what's called a deployment, and this is based on the deployment config, and it tells it to go essentially create the actual pods that are going to represent your application, right? And sometimes this can be very, very complicated. We do very, very complicated deployments, for example, monitoring with the Elastic Stack, and so you can actually do things like with what's called a deployment pattern, where an actual pod kicks off that actually tells about, like, basically talks to the Kubernetes API and tells certain things to fire up at certain orders. And in fact, coming down the pipe in OpenShift, we're going to have an Ansible deployment pod or deployment image that will then be able to like do very sophisticated upgrades to your application. And so you end up in these scenarios where you're like, oh, I need to update the database first, then update the web server, then go back and update the schema on the database. And you can end up in these kind of orchestration upgrade problems. And that's why you have this deployment pattern where you can kind of define these things to happen. But in its simplest case, a deployment just says, hey, go fire up new versions of the same image, right? Don't change the application definition at all, but just go create new pods based on the new images that have just been created. And so then what will happen, it'll say, oh, okay, replication controller represents the old images. It will go down to 0. Replication controller with the new images may scale up to 1 or maybe 2 or 3. And then there will be pods living side by side for some time. The old pods will die off, as traffic dies off or bleeds off, and new pods will be created. Now, I mentioned in this application definition, you can also have essentially YAML or configuration that describes the persistent volume. So if you were firing up a simple application like HTTPD or Apache and MySQL, you could define both of those and also define the storage that they need. You can also define the service and the name for the route. So if it's www.example.com, and you want to expose it externally, but you don't want to expose the database, you may only expose the web server with a route, but the database will just have a service, which is kind of internal. And then essentially, once you've defined all that as I mentioned, in an OpenShift or Kubernetes YAML file, you can move that between clusters. And you can now imagine that since I've standardized on this essentially object model where I can define all these things, as long as I have the right amount of storage in different clusters, including I could have a cluster on a developer's laptop in development and production, I can just move that Kubernetes YAML file between those, and it can actually have all the information it needs to build all the images and deploy everything. You may need like a base image, like say something like Red Hat Enterprise Linux, but you could actually define how to build everything just from that. So I hope this gives you a pretty decent overview. We're going to dig deeper into this in the lab.